All right, the next talk is by Christian Marois from NRC, and he will be talking to us about spiders as a habitable worlds observatory experiment. Thank you so much.
Okay, yeah, I think that's working. Hello everyone, so today I'm gonna present to you a fun experiment that we did, just to have fun, because we had to wait a couple of months for Subaru to be ready to receive Spider. And since the Habitable World meeting was up there soon, we decided to test something to try to use Spider, which is a 10 to the 7-ish contrast coronagraph, an experiment. But we do have an imaging Fourier transform spectrograph, so we can take spectra on each pixel up to R20,000. So we said, well, let's try to dig a dark hole, 10 to the 7, and then take some images with our imaging Fourier transform spectrograph and do this polychromatic analysis and see if we can reach habitable world level contrast using high dispersion spectrograph. So Spider is an instrument built by NRC in Canada and Victoria. So this is the instrument, and we shipped it to actually Subaru at the end of October on Halloween. It's called Spider, and we ship on Halloween, which is great. So we told the team that we're getting the Spider out of the building for Halloween. And we installed it at Subaru with Julien. It's amazing to work with Julien and Olivier at Subaru. We installed this in 3 days. It went super well. It's amazing to have access to such a facility in the mountain as well. And we did dark hole on sky, so it was a lot of work, but it did work, and we managed to get some decent data, even in some horrible conditions. But we did show that it works. So that was really amazing. So there's a bunch of poster and talk that we had this week. So I learned coming here that this is a 20-year of ADI celebration. So wow, that was amazing. So Remy and I took a nice picture to celebrate this event. And then we saw Carl's and GB's slide about all the amazing work that people have been doing in the field since then, coming up with new strategies, machine learning, etc. And then suddenly we felt a bit like this. So yeah, we're getting old, but amazing students coming in the pipeline, and great ideas to try to improve this. And that made me realize that in 2028 it's going to be the 20 years of BetaPIC, HR799, and FOM a lot. So maybe we should do something, and so people don't feel bad of showing HR799 in their talk or putting movies and stuff. So people will feel included of presenting HR799s. So we heard this week, we had a bunch of talk about interferometry with gravity, that they are friendly fringes. So they are the fringes that you design your instrument that you want to see. So these are very friendly fringes. And then we also learned from a KPIC experiment and also from gravity that there are less friendly fringes. So they're the one that you don't want in your instrument that are messing up your data processing. So you can see I have very good talent of graphic and PowerPoint. So that's the extent of my, my artistic sense. So Spider has been built over about 3 years. A lot of team members here. We have Adam, William, We have Adam, William, Caitlin, and Andre. Mamadou developed our chronograph. We're collaborating with Julien and Olivier with Skexeo. So it's an instrument that took several years of work with engineers at NRC, like Olivier Lardière and Jolef. So it's a lot of work from a lot of people to get us to this point. So what does it look like? So we have a simulated source. We can take light from an internal source or the telescope. And then we have an APLC coronagraph with an Alpha ODM 468. And we have a focal plane mass here. And then we split the beam in two. We have a self-covering camera from Pierre Boudreau and all that we have implemented using the fast focal plane mass from Ben Gerard. And we send the light to an FTS. That was a lot of work from our student and our PDF, Adam Johnson and William Thompson as well, to get to work. And then the back end, we have a photon counting camera, the Saphira, which is not fully working yet. So we're using a CRED 2 at this point with a lot reduced sensitivity, but we can still do a lot of research on the bench with a bright laser. So the FTS was great. Is you get your dark hole, you get your image, and then you get the spectrum per pixel, which then you can do post-processing. You can do CDI with this path. We can do SDI. And of course, the SCC with the front-end system here. So basically, the idea is to get roughly, this is roughly what NDES and other instruments are thinking, getting down to about 10 to the 5-ish contrast, and then put underneath a high-resolution spectrograph and get down to 10 to the 8, 9 contrast using polychromatic analysis. So, but as far as I know, nobody has ever tried this on a bench to be able to confirm that we can actually do this kind of processing and reach this kind of contrast. And I have to tell you that Spider has not been designed to do this, so don't be surprised that it does not work, as we thought. So we can say that we're spreading the wings of Spider. So thank you for AI. We can now generate a bunch of these images very quickly. And Bruce is not here, so it's OK to show Spider on screen. So images. So we have on our SCC pass, we have a 1.5% filter in H-band. So we dig a dark hole about a few times 10 to the -7. We see a small ghost that's incoherent that we cannot take out with the SCC. And on the left, this is the same field, the same image as seen from our imaging Fourier transform spectrograph, where we pose the loop, and then we just blast the laser at full capacity so that we can actually scan and get a good SNR. So we're seeing the same ghost here, and the contrast is about 2 10 to the -7 away from that ghost. So then what we did is let's simulate habitable world. Let's assume that this is a visible band image. So we split the 3% band pass of the FTS in 3 1% band, and then generate these 3 images. And then what we do is just try very simple difference. This is what I was doing as a grad student back 20-something years ago. So I still like these. This was basically my Trident instrument for my PhD. So we had combined these into simple and double difference. And oh, what a surprise, it does not work. We're seeing a lot of evolution with wavelength and can't really get anything close to habitable world contrast. So we said, well, let's boost the contrast and go to R3000 and see what we see. So it's going to take a few seconds to go through the data cube. And you can take a look in this region. This is the weird incoherent ghost. And when you go to R3000, you start to resolve the interference. So while this ghost was incoherent in a 1% bandpass, when you go to R3000, you start to resolve the interference and what's going on at that location. So basically what's happening is we have some surface somewhere that's creating some kind of ghost, and then that ghost, which is probably a copy of the point spread function that's off-axis and very dim, start to interfere with speckle, giving that the optical propagation, so this is the speckle, you can think of, whoa, this is really weird. So this is the speckle propagation length, and the ghost has seen a little bit of extra optical path. So there's what we call an OPD. There's an extra length in the propagation of the photon, and that's produced what's called an OPD. And this jump of offset generate what we call a chromatic effect. It's basically the electric fields start to spin, and then you see these weird up and down interference. So if you look at the SCC pass where we have a 1.5% filter, what we can resolve in terms of Currian slants is about 100 micron, and it turns out that this weird ghost we're seeing is also 100 micron. How unlucky can you be? And then when we went to R3000, now we can resolve Currian slant about 4 millimeter, and now we can fully resolve what's going on. So the 100 micron get resolved, and this is why we can see all these nice associations. So another way to say this is that we started with a very crappy speckle field. This is before closing the loop. We had a very faint ghost, and then we closed the loop, and now the speckle went away, but the electric field of the speckle and the ghost started to interfere together, and this is why we can't kill speckle at that location. So if you take 1 pixel and you look through wavelength, so this is wavelength and intensity, the speckle inside the bandpass is oscillating in intensity, so basically it means the electric field is doing this, and there's no way with a differentiable mirror to be able to kill that speckle. While if you go into the IFTS, which has a very narrow spectral resolution, now this is the middle part, then the electric field is mostly constant, and you can really go through and see the entire electric field change with wavelength. So if we would take only 1 slice, we could probably do a much better dark hole in the very tiny bandpass, is kind of what it's telling us. So basically, the higher the spectral resolution, the more chromatic your speckle can be. It's much more complex than just a Fraunhofer or a Fresnel propagation. So it's basically still Fresnel and Fraunhofer, but you need to account for different wavefront coming at different angle, reflecting in coatings and stuff. So as you go to higher spectral resolution, you start resolving longer coherence lengths. So you need to be careful of photon scattering and coming back in your science path. And you can have tens and tens of millimeters if you're going to extremely high spectral resolution. So basically, you need to be careful with what kind of optics you put in, what kind of coating is on your optics, and be very good with your baffle. And of course, try to avoid any glass if you can. So give you an idea, if you go to GAR 100,000, you can go up to 150 millimeters. So this is getting very, very long optical length, and will start messing up and generate what we call some fringes in your images, which was seen by KPIC and other instruments. As they only see this in one point, which good with SPIDER is you can see the entire field and all the fringes, and also see the spatial correlation of the fringes. So if you go to R9000, we said, well, we sorted out the problem, we know what's going on, we have a little ghost, everything goes well, let's go to R9000, it's going to be even smoother, and you can do SDI and achieve a habitable world contrast. And what a surprise, we see a Christmas tree start to oscillate everywhere. And our first reaction was, what the hell is going on? So the next thing we did, so you could extract some flux of some of the speckle in your dark hole, and you're seeing all these weird associations. So this is the very slow evolution that we saw. This is the ghost that we saw in the short band images that was evolving very slowly. But if you go to R9000, you start to resolve another contribution, and all this signal is real. It's not noise. The noise is way below there. So this is all coherent stuff happening on the bench. So if you do a Fourier transform, you can see peaks, which is very similar to what KPIC and gravity showed. You see these peaks, and these are the fringes, the fringe effect that generate extra chromatic signal that prevent you to do a very good extraction of your spectrum. So one thing you could do is you can actually take your images as a function of wavelength, and then take the derivative of the signal as a function of wavelength. It's going to tell you how the flux is evolving between the spectral channel, and you see these waves going through. So basically what's happening is we have some kind of flux coming in at an angle, and you see the spatial OPD of the signal, which is really cool, and you can use all this information as a function of wavelength and space to derive the OPD of the ghost, the angle it's arriving, and the direction it's arriving, so you can then work on your bench to try to come up where it's coming from. So we can then, and the good idea by William is then we took our data cube, and let's do something absolutely crazy and unrealistic, and assume that all the planet light comes from one slice of the data cube, and then you use all the rest of your data cube at R9000 as a reference. So now this is like observing a laser planet, I guess. And then let's try to see if we can combine these references to gain in contrast and see if we can reach 10 to the 10. And we still were not able to. So we reached about 4 10 to the 10 in the very small 2 lambda-Verdi patch, which is the best of the dark hole. Well, we did manage, again, about 36, but that shows that if you're thinking of developing a basic chronograph and put a high-resolution spectrograph behind it, to reach 10 to the 10 or 10 to the 8 or 9, it will not be that simple. You need to make sure you design the instrument basically to make sure that it can achieve 10 to the 8 contrast. So we're planning a lot of work. So we did not spend a huge amount of time to try to do better because we want to upgrade the instrument. We had fun, and then the problem of when you have fun, then you open a can of worms, and then, oh, I want to make the instrument better now, so then you need more money and more proposal and et cetera. So now I'm at that level. And we're going to try to do some more work on CDI and SDI on this. So I'm going to stop here. So overall, doing high contrast imaging, combining a medium-level instrument with a high-resolution spectrograph is not as simple as Fourier transform, Fraunhofer, DM control, and chronograph design. You also need to account for scattered light ghosts in your instrument and understand how they're going to impact your high-resolution spectrum. Thank you.
Question, if anybody has one quick question. So Spiders has now been shipped to Subaru.
Yes.
So is the plan to keep moving forward and using it as a test bed once it comes off of Subaru, or is the plan for it to stay there?
Oh, that's a long question to answer. But the 10-second is we have 4 half-nights coming out with Skexeo Engineering at end of May and June. After that, the goal is, what we were told is there's another instrument coming, so we might have to come back to HA. So if you have a telescope access somewhere and interested to work with us on Spider, please talk to me.
Great. Awesome. Well, let's thank
Thank
the
you.
speaker again.